Welcome everybody to Algebra 2. Today we've got a bonus section in Chapter 9, solving trigonometric equations. Now this is something that is not included in your textbook, but it is an important skill as we look forward to the trig pre-calculus class that we will be taking next year. And a lot of this is really taking information that we already know and using it to solve some equation that has a trig function in it, but we're typically going to be solving for the angle. So we're trying to answer what is the angle that satisfies this relationship. Now, you may be saying, oh, if we're trying to find an angle, don't we use the inverse trig functions? And you're correct to a certain extent. Inverse trig functions, they work out really well when we're talking about a right triangle that is in like a real, it's just a geometric construction. But when we move to an XY coordinate plane, you'll find that using an inverse trig function doesn't give us all the solutions. And that's because inverse trig functions have limited outputs. So I've given you that limit that is set on the outputs, and it's designed to give you an angle that will come out to fill in one of those triangles, one of those geometric constructions, as opposed to answering an X and Y equation. Okay, depending on where the reference triangle for an angle is, there could be more than one angle that produces the same trig output. So we're gonna take a look at that on the next slide. So our steps to solve a trigonometric equation is, first of all, isolate the trig function. Okay, that may mean factoring or taking the square root or just using basic algebra steps. Second, we want to draw the appropriate reference triangle or triangles. There may be more than one, and there may be a quadrantal angle there. We need to know what quadrants are those angles in. And then lastly, from the positive x-axis, what angle will lead us to the hypotenuse of those reference triangles that we've drawn in. Okay, and we want to be careful, we want to understand our special right triangles, what angles are inside, and also what are the quadrantal angles, the angles that lead us to an axis. All right, so first of all, how do we decide where our reference triangles are going to go? Now, there are some mnemonic devices that will help you, but that's a lot of memorization. And these are listed in your textbook, but from an earlier section, but they're really something that I hope we can conceptualize instead of memorize. That's kind of a running theme that we have here. So to know our quadrants, first of all, sine, the sine function, is the y value, right? We said it was y over r, and on the unit circle, r was 1. So sine is y, and that's the height of the triangle. So what we're going to do really quickly is if we have a positive sine, then that means our reference triangles will have positive height. They'll be up in quadrants 1 and 2. Okay, likewise, if we have a negative sine, then our triangles will have negative height. They'll go down into quadrants 3 and 4. All right, next, cosine is the x value. That's left and right. That's what the x-axis measures. So if we have a positive cosine, then our triangles will go off towards the positive x-axis. And if we have a negative cosine, then our triangles will go to the left. They'll go to the negative x-axis. And then lastly, tangent is y over x, rise over run. It's the slope of our hypotenuse. So if we have a positive tangent, then our hypotenuse is going to be sloping up to the right. We'll be in quadrants 1 or 3. And if we have a negative tangent, then our hypotenuse will slope down to the right. Our reference triangle will be in quadrants 2 or 4. So again, just understanding what the different trig functions mean, really, really helpful to drawing those reference angles in a hurry. Then we can start labeling and figuring out what angle is produced, actually solve the problem. So let's get started. We're trying to find all the solutions on the interval between 0 and 2 pi. So our answers are going to be angles that are in radians. And let's just get after it. So the first one, 2 sine of x plus root 3 equals 0. I want to isolate the trig function, so I'm going to subtract root 3 from both sides. That means 2 sine of x equals negative root 3. And then I can divide away the 2. So sine of x equals negative root 3 over 2. Well, let's construct that reference triangle, or more than one reference triangle. My sine is negative, so that means the height of my reference triangle should be negative. I'm down in quadrants 3 and 4. And the sine ratio that is produced is opposite over hypotenuse. So from the angle at the origin, the opposite is negative root 3 in both triangles, and the hypotenuse is 2 in both triangles. And that should be enough information for us to label the third side, because it's going to set up a special right triangle. And here you can see we've got a root 3 and a 2. That means both of these triangles have a missing leg that is length 1. One of those legs goes in the positive x direction, the other in the negative, and that's where students will typically make a mistake. They'll miss that negative sign. So be sure that you're checking that if the legs are going x and y in negative directions, that you label them with negative signs. Okay, now to actually solve for x, I'm going to start in the positive x-axis and say, okay, how far would I rotate to get to that first hypotenuse that makes our first reference triangle? Okay, so there's my first solution. Well, I need to think, okay, if I have root 3 and 1 and 2, then the reference angle inside is going to be across or opposite the root 3 leg. It's going to be a 60-degree or pi over 3 radian angle. So I've gone a full pi radians and then pi over 3 more. That is 4 pi over 3 radians for my first solution, and I do get a second solution. If I start on the positive x-axis again, and this time rotate all the way through, it's a full circle, but I stop 1 reference angle short. So I'm pi over 3 short of a full 2 pi radian circle. That's 5 pi over 3. And those are our solutions. We are done with this problem. All right, for our second example, 2 times cosine squared x. Well, if we ever see a trig function squared like this, and notice how it's the cosine that's squared, that means the same thing as taking all of cosine x and squaring it. Okay, now they write it that way so that you don't confuse let me try and speak this in English. They don't want you to read this as cosine of x squared and misinterpret where that exponent is going. So that's why they write the exponent directly on the cosine. It's the function that's being squared. But our process stays exactly the same as it has before. We want to solve for the cosine function, isolate that, so I'm going to divide both sides by 2. So cosine squared x equals 1/2. And to isolate cosine fully, I need to square root both sides. And whenever I square root both sides, not only does it cancel out that square on the left, but it produces a plus or minus situation on the right. And I square root the top. Square root of 1 is 1, and square root the bottom, square root 2. Now this is not going to be my answer, so I don't need to worry about rationalizing the denominator there. This is just kind of a stepping stone towards our final solution. Where could cosine be positive or negative? Well, I could have a positive cosine here, a negative cosine here, another negative cosine here, or a positive cosine over here as well. So I get 4 places on that on my xy plane here where that happens, where I get a positive or negative. But let's label those triangles. Cosine is adjacent over hypotenuse. So I've got 1 over root 2. I could have negative 1 over root 2. Down in quadrant 3, negative 1 over root 2. And in quadrant 4, 1 over root 2. So hopefully we're seeing, hey, 1s and root 2s, those are 45, 45, 90 reference triangles. Let's label those sides that are missing and put the negative signs in place if those legs are going in negative directions. 4 reference triangles means I will have 4 solutions in that one rotation around our 4 quadrants here. So if I start on the positive x-axis, This first rotation, well, let's think about what our reference triangle is. Well, if it's a 45, 45, 90, a pi over 4 reference angle is happening at the origin. So pi over 4. Then in the second triangle in quadrant 2, I rotate all the way over to that hypotenuse. That is 3 pi over 4. Right? Almost to 1 pi, but not quite. I'm a reference angle short. The third one, here I go 1 reference angle past pi. That's 5 pi over 4. And my final solution, I am pi over 4 radians, 1 reference angle short of a full 2 pi radian circle. That's 7 pi over 4. So we have 4 solutions for this equation. Okay, now I'm going to take a little bit of a side note here. If you wanted to, you may look at this and say, oh man, that's an equation I don't know how to do. Will that life hack method work using the graphing calculator? Is that a way that we could check? And yes, it is, but we need to be very careful. So if we're going to check in a calculator, we need to do a couple things. First of all, we want to make sure that the function is entered into y1 and the other side is entered into y2. So that's how we would type those functions in. Secondly, they're telling us that our x values are only going between 0 and 2 pi. So I'm going to have to change the window to go from an x min of 0 to an x max of 2 pi. And we may have to do some zoom fit or something once we have that window established in order to see the intersections happen. And lastly, we want to make sure that we are in radian mode. But if we type that in and we actually take a look at it, what we should see is a situation where we have a cosine function being squared. So it kind of looks like this. And then our value of 1 going across like this, it does intersect 4 times. So we will, if we do calc intersect on that, we're going to get a bunch of decimals. We would have to check and see, are those decimals matching what these answers would be as decimals? So it's a little bit involved, but it does still work. It's kind of nice to check that graph and say, okay, how many solutions should I be getting between 0 and 2 pi? At the very least, that's a nice check to have. But that's how we can use technology to help support our answer. Our next example, here we have a tangent function. All right, let's isolate that trig function. I need to subtract 1 from both sides. That means root 3 tangent x is equal to -1. Divide away the root 3. And we've isolated the trig function. Tangent x is -1 over root 3. And again, that's not my answer, so I don't need to worry about rationalizing the denominator with that. It's just going to help me draw and label my reference triangles. All right, the trig function I'm using is tangent, and its ratio is negative. Well, that means a negative sloping hypotenuse. My reference triangles are going to happen in quadrants 2 and 4. So go ahead and draw those reference triangles in. Tangent is opposite over adjacent, opposite over adjacent, opposite over adjacent, down there in quadrant 4. We see 1s, we see root 3s. We should be able to fill in those missing measures because they make special right triangles. Hypotenuse lengths of 2. All right, now to actually answer the question from the positive x-axis, what angles lead me there? Well, think about our reference triangles that we're dealing with. The reference angle that we're looking for at the origin is a pi over 6, a 30-degree. Right, we're setting up 30, 60, 90 right triangles. So my first solution rotates from the positive x-axis to that first hypotenuse. And if it's pi over 6 inside, I'm going almost all the way to 180. I'm stopping pi over 6 short. That is 5 pi over 6 radians. And my second solution, I'm going to rotate all the way around almost a complete circle. But again, I'm going to stop 1 reference angle short. So that is 11 pi over 6, almost 2 pi. That's all there is to it. Really, really good way to go through and practice using those special right triangles and to learn the different fractions involved with special right triangles having radian measures. This is really, really good practice. I hope that you're devoting some time to learning these through experience. It's a really, really good experience. All right, our next example, cosine squared plus 2 cosine x equals 3. Well, this is a little different. We don't just have a single cosine function. I would hope that you would relate this to having, when we're solving for x, that x squared and 2x equals 3. If you were going to solve that for x, I would hope that you'd get it set equal to 0 and try to factor it. Well, we're going to do the same thing, except instead of x's that we're solving for, we're trying to isolate the cosines. We can do that. So I'm going to get it set equal to 0, because if I'm thinking of it like it were x's instead of cosines, I would want to try factoring. And that's exactly what I'm going to do here. I hope this works out. So my factors, again, they're not going to have x's inside. They're going to have cosine x's inside. And hey, look at that. Plus 3 and minus 1 will do it. All right, and now I just have two little equations, two factors that could equal 0. So cosine x plus 3, where could that equal 0? If I solve it, isolate the cosine, cosine x would equal negative 3. And that's not setting up any special right triangles. I would hope maybe we think of that as negative 3 over 1. Okay, my cosine would be negative in quadrant 2 and quadrant 3. And that's adjacent over hypotenuse. But wait, something's wrong there. The hypotenuse is supposed to be the largest side of a right triangle. We get no solutions out of this because that right triangle is not constructible. Now, all is not lost. We still have this other factor here that will work. Let's set that equal to 0 and solve. If I add 1 to both sides, where can cosine x equal positive 1? Well, think about it. That means x over r is 1 over 1. So the only place that could happen is if I'm all left and right, just going to the right. I get the solution x equals 0 out of that. That is the only solution I could obtain. And if I were to go through and try that with the life hack, I would only see one intersection happening right away. Other than that, those graphs will not intersect. Okay, and our final example, here we've got different trig functions acting together. We've got tangent x times sine x minus tangent x equals 0. Holy cow. Well, this is another example where we need to factor in order to isolate the trig functions. In this case, we can take a GCF of tangent x out. It's already set equal to 0, which is a really nice benefit. That would be really tough if they didn't have it set equal to 0. Probably be difficult to figure out where to begin this problem. So the first factor, tangent x, where does that factor equal 0? We've isolated that trig function through factoring. I think, okay, tangent means slope, so I want to know where can I set up reference triangles that have 0 slope? Oh, well, I could either be going to the right on the x-axis or to the left. That's where x would equal 0 radians or pi radians. Let's try our other factor. Set that equal to 0 and solve. All right, where does my sine equal 1? Well, I want to know where y over r is 1. We know r is 1 on our unit circle. That only happens if we're straight up in the positive y-axis. That would be the angle x equals pi over 2. So our set of solutions, our three solutions that we get out of solving this equation is x could equal 0, pi over 2 or pi radians. Right? Oftentimes where students make mistakes, again, leaving negative signs off their reference angles when they draw those in, drawing the triangles in the wrong quadrants, or it's the algebra when it comes to factoring trig functions or something like that. Sometimes they can't get the ball rolling with that simple algebra. So just recognize that we can use algebra even if we're dealing with functions, so we can still factor them like we see here. But if we follow those 3 steps and we understand the radians and how to construct the reference triangles, and we know what our ratios are for special right triangles, we're going to be in really good shape and get some quality practice out of this. And we are definitely going to have a leg up when we go into trig pre-calc next year. All right, that does it for the examples. Your assignment is a worksheet for this 9-point B lesson.